Okay, hello everyone again. Just to come back to the question on the intuitive way about the I new cube, it basically comes from this. So I over new cube is just the phase space density, and phase space density is conserved because this is just conservation of photons. I mean, these are obviously constants, so they're not relevant. And phase space density is conserved simply because you don't create or destroy photons. So they have to be somewhere. Liouville theorem. Okay, so coming back to all right, so how do we do radiative transfer in practice? As I promised, yeah, it's a little bit more complicated, but it's not too bad, and we can go over it, or some of the bits of it that are important. So the first thing that you need is some kind of description of what happens with the atoms when they get ionized or when they recombine. So this is something we refer to as chemical reactions. I don't know if chemists might disagree. I mean, there are different kinds of chemical reactions, but because these involve essentially changing the outer layers of the electrons of the atom, they are essentially chemical reactions for us. So that's what we assume. So you have reactions like this. You take two species, you can get third, or maybe get two and get two others, and so on. So if you have this kind of reaction, then you can describe it as the rate of the number density change of the new species over time is the number density of species A, number density of species B, and then some kind of velocity average cross section, which we call coefficient, rate coefficient. So why do we have number density of A and B? Is because an atom of A needs to meet an atom of B in order to create C, right? So it should be proportional to number density of both A and B because it's a two-body reaction. And this kind of rate coefficient is actually quite complicated to calculate properly. You need quantum mechanics and scattering, and it's a bit of a pain, but thankfully there are many people who do this sort of stuff, so we can usually have reasonably reliable rate coefficients to use. And these are just number densities of different species N. So what are the processes that we are interested in? Well, the main one, of course, is just photoionization, in which case we have neutral hydrogen meeting photon, and then you get ionized hydrogen and an electron. So that's the reaction. So the change in the the ionized hydrogen density, either increase or decrease, is just the neutral density of hydrogen, the number density of hydrogen, neutral hydrogen, and then number density of photons, which can be calculated based on the energy of the photons, as we discussed in the previous part. So essentially it comes as a average intensity times the cross section and divided by h nu. So this is called photoionization rate, and this multiplies the number density of neutral atoms. So this here is the number density of photons. Why? Because you have the energy density divided by the energy per photon gives the number density, because total energy divided by the energy of one gives you how many you have. Photoionization rate is, well, just the cross-section times the number density times the photon number density. And you need to integrate from ionization threshold of hydrogen, because photons that are below the threshold cannot ionize hydrogen, so we don't care about them in this context. And for a point source, you can write photon flux, which is the luminosity over h nu, and then the optical depth attenuation integrate it over all frequencies, and then attenuate it with over the sphere, as we discussed earlier. Then the photoionization rate is the same thing, basically, but with the cross section as well integrate. It's very similar integral. So photoionization cross section, as I was discussing before, it's a little bit complicated. You need quite a bit of quantum mechanics to actually calculate them properly, but the process is quite simple. You have a photon coming in, gets absorbed, kicks out an electron if it has enough energy, and then any excess energy goes into the electron and possibly a little bit into the atom to conserve momentum. And of course, you need to subtract whatever binding energy of the electron was. And the cross section, when you calculate it, looks actually quite complicated because it depends on where the ionization happens, and there are particular frequency at which it jumps because of that. These are the ionization ages because of the different atoms and different levels that you can have. But roughly speaking, the photoionization cross-section goes down with frequency as roughly as the cube, typically, of the frequency. Then there are some other reactions which you need to take into account. Collision ionization, so it's similar to photoionization, but in this case you have neutral atom being kicked by free electron. And if the electron has enough energy, it can kick out another electron, so you get two electrons and an ionized hydrogen atom. So this kind of process is again two-body reaction because you need the electron and you need the neutral atom. So it's proportional to the number density of the neutral atoms, number density of electrons, and some kind of collisional ionization coefficient, which again you need to calculate using quantum mechanics, and it can be done. And it depends on temperature because higher temperature means higher energies for the collisions and so on. Then there is recombination, which is just the opposite to ionization. So you have ionized atom, electron combine, get neutral atom, and emit a photon. In this case, you have a recombination coefficient, and then the number density of electrons, number density of ionized atoms. And this coefficient is dependent on temperature weakly. So it depends, but not very strong way. There are some kind of fine points here. So this coefficient here could be either so-called case A or case B. So case A is when you have non-local absorption. So basically the photon gets emitted, but then it travels some distance away and may be absorbed somewhere completely different. Or you can have case B, which is simpler because you assume that the photon gets emitted, but then almost immediately gets absorbed in the same place, which makes things somewhat easier to calculate because they are very local. Everything happens in one point. So usually in codes we use case B, but in practice sometimes case A is the relevant one. So you need to be careful with this sort of thing, and there are papers on this stuff. Okay, so if you have all these reactions, we can combine them together. So first of all, we can define ionized fraction, which is usually the quantity we're interested in. So the ionized fraction is obviously 1 minus the neutral fraction because the total fraction of atoms is 1, and they are either ionized or neutral. And this is obviously the number density of ionized atoms divided by the total number density of atoms of hydrogen. And then the chemistry equation for hydrogen only becomes ionized fraction over time divided derivative with respect to time is the neutral fraction, photoionization rate, collision ionization, and recombinations. Now that's the equation that we need to solve. So normally that's not very simple equation to solve even this relatively simplest case of hydrogen only. But one thing that you can notice is that you can, if you have an equilibrium, so nothing changes over time, then this derivative, of course, becomes 0, and you can solve for x. Not very difficult. And what you get is that x is some combination of all these quantities. So in equilibrium, it's easy to solve. You don't need to do a differential equation, anything. You just can write it down. As long as you can calculate how many photons you have, you know these coefficients, they only depend on temperature, and you can calculate what the state is. So for example, you pick, say, 10,000 degrees temperature, and you can calculate this is about 1/2 or so. However, equilibrium is not a good assumption very often. So instead, what you need to do is not solve this, but you need to solve the full equation. And in principle, that equation doesn't look that hard, right? Except it is. So why is it hard? Well, first of all, it's not a linear equation. It looks linear because you're solving for x, and x is only here and here and here. But you need to remember that the number density of electrons also depends on x, because that's where the electrons come from. They come from ionizing hydrogen. So in order to have an electron, you need to ionize some hydrogen atom somewhere. So this means that Ne is also dependent on x, so this whole thing is nonlinear. And not only nonlinear, but it's actually so-called stiff equation. So stiff equations are hard to solve. I am not going to actually discuss this much. We can discuss it later if you're interested. But there are special methods for solving stiff equations. So there is no very clean mathematical definition of what equation is stiff and what isn't. But roughly speaking, it's an equation where there are several very different time scales involved. So if something evolves on very small time scale, very short time scale, and something else evolves on a very long time scale, and you have both of these scales in your system of equations, you get a stiff equation. And that's a problem numerically. Why? Because if something evolves on short time scale, your numerical method wants to take very small time steps in order to follow that very quick evolution. But this means that anything that evolves on the long time scale will be now evolving very slowly with very many small time steps, which you think, okay, well, that's what you need to do. But in practice, what happens is the quick evolution leads to some kind of equilibrium on the short, quickly evolving thing. But now you need to go very slowly over something that's not evolving very quickly, so it's very inefficient. Basically, you can take long time steps, but your method doesn't allow it. I don't know if I can explain it very well, but you can have equations where the solution is something like, for example, e to the minus x plus e to the minus 1000x, right? Imagine that's a solution for your equation. It's easy to write equation that this is the solution. So this term, as x evolves, this term very quickly becomes irrelevant, right? Because 1000x, if x is anywhere bigger than 0, it's basically 0. So the solution will be this, but you still need to evolve on very, very short time steps because this is changing very quickly, even though it's irrelevant, which leads to really inefficient methods. And that's exactly what happens with pretty much all chemistry equations like this. So they are hard to solve. There are special methods for solving this kind of equations. They're well developed, but you still need to do a lot of work. These are called implicit methods for solving differential equations. If you're interested, then you can read more about this, but they are expensive computationally. And what makes things even worse is that it's not one equation typically. If you really want to do full job, you need to solve many equations because it's not just hydrogen. We already had the hydrogen, right? But you can have other pieces like ionized hydrogen, or you can have helium, you can have ionized helium, you can have twice ionized helium, you can have hydrogen molecules, and then you can have also metals, all sorts of other heavier elements, and it very quickly gets very complicated. You need to solve many, many, many equations, and they're all hard, and if you have many of them, that's much harder still. There is H1 as well, which usually is in equilibrium, so that's why you can write like this, but again, it's very complex. But that's what we need to deal with. On top of that, there is additional complication, which is that you don't need just the chemistry equations to solve for the ionization state, but you also need to solve ideally also for the temperature state of the gas. Because radiation, as you are ionizing, you also heat it. Why do you heat it? Is because when you ionize, usually the photons are not at exactly the right energy to kick the electron out. They typically have more energy than that, right? Because you just have excess energy, and this excess energy goes into heat. And this heat will be heating up the gas. So that's called photonization heating. And there is also cooling, which is, there are many processes that cool the gas. So overall, in order to get the temperature state or the internal energy evolution over time, you need to basically calculate the evolution based on the heating and the cooling of the gas. And the heating comes mostly from photonization, but also can have also X-rays, Compton heating, Lyman alpha heating, depends on the physics you're including. So the heating coefficient, the heating term is basically the flux times the cross section, and then you have the difference between the threshold and the photon energy. It's very similar integral to before. The only difference is that now you put here the difference in the energy, because only the excess energy is heating the gas. The photonization energy gets absorbed just to get the electron out of the atom, so it's lost, right? This is the binding energy of the electron. Okay, so you have to do all that, and then you come to doing the radiative transfer. So when you are doing the radiative transfer, it's a hard problem to do. It's computationally expensive for several reasons. So first of all, it's a non-local process. What does this mean? It means that if you have a photon emitted here, it may be absorbed somewhere else entirely, which is usually not the case if you do, for example, hydrodynamics or something else like this, because hydrodynamics is very local. It works by atoms interacting with each other locally. So hydrodynamics here usually doesn't have much to do with hydrodynamics somewhere else. So it's quite local, and you can calculate the fluxes for each cell and then calculate the evolution. Not that it's easy, it's still not easy, but it's at least local. Radiative transfer is not local. Sources could be here and shining to the end of the universe, right, in principle, unless something is on the way. The other thing that's problematic is you have 6-dimensional space. So normally, if you do, for example, hydrodynamics, you do it in 3 dimensions, right? And maybe also velocities. Here you have 6 dimensions because you do the 3 dimensions of space, but you also have 2 dimensions that show you the direction. Since all the radiation has direction, you need care, is it emitted your way or some other way, right? It's completely different. So you need to take into account the direction. It's not a local thing. And there is, of course, time, so total 6-dimensional equation. And 6-dimensional equations are hard. You cannot even imagine 6 dimensions, let alone solve things in 6 dimensions. Right? In 3 dimensions are hard, 6 are much harder. So essentially, you need to do a lot of approximations to make this feasible. Otherwise, it just cannot be done. So what are the approximations? Well, we'll discuss them in a moment. But before we get to that, just to introduce you quickly, we had this exercise of comparing different codes, which happened, I think, quite a long time ago, about 16 years ago now. But anyway, so we came together and started comparing different codes. So why would you do that? Is because if you are solving the radiative transfer equation and you inevitably have some approximations, then the question is, okay, so am I getting the solution correctly? Because it's not the exact solution. It's not perfectly correct. You know it's not perfectly correct because that's impossible. So then the question is, okay, so how do I verify that what I'm getting is at least sensible? Maybe not perfect, but at least good enough. And there are two ways to do this. Either you compare to an exact solution that you know, and there are a few of those, but there are not that many because radiative transfer is hard. So solving the equation exactly is also hard. You can only do it in kind of very special idealized cases. Or what you can do is, okay, compare a bunch of different codes. And since they have all different systematics, different methodology, different approximations going on, if the results of them are at least roughly comparable, then maybe you are on the right track, because you may be making a mistake, but the other code is making some other mistake. And if your results still agree, this gives you some confidence that they're actually working correctly. So that was the basis of this kind of comparison. And we did this. So there were, in this case, 9 different codes. And the problem here is the simplest possible. You put a source in the corner. So the source is starting to blow out in all directions. Obviously, since it's in the corner and we are only calculating this area, 1/8 of the box, it becomes, well, it's just a section of a sphere. And this sphere expands over time and gets bigger and bigger. And you can see already that spheres are similar, but they are also not the same. Right? So we already can see without even thinking very hard about it, that there are some issues. If the results are not all the same, clearly they cannot all be correct. Maybe they are all wrong, but they are certainly not all correct, right? So we need to understand, okay, so what is reliable, what isn't, and how do we interpret the results of. So for example, some of them don't even make quite a sphere, right? So that's already a bit of a problem because it needs to be a sphere. It's a symmetric situation. So that's one thing. Some of them make it much thicker transition than others. So this one is thinner, this one is thicker. So why is that? And there are things like this that you need to worry about. On the other hand, all the spheres are the same size. So that's very nice because this means that all the codes conserve photons, because the size of the sphere is determined by how many photons you emit, because this number of photons ionize a certain number of atoms. And if your sphere is the right size, this means you ionize the right number of atoms. So there is some agreement and some disagreement that you need to discuss and so on. Okay, so the main classes of methods, and there are examples of both here, among those is either ray tracing, which includes so-called Monte Carlo methods, which I'll explain in a moment, and so-called moment-based, which comes back to these moments of the radiation that we discussed in the first lecture. A bit of an aside, there is something called ray tracing also in graphics and video games, which I'm sure you have seen and played with at one point or another. So your computer is doing a lot of these calculations so that you can see these nice reflections and have realistic looking worlds and weapons and whatever. That's a different problem from what we are trying to solve. Here it's mostly essentially reflections and points of view and things like this. And it's much less, I mean, obviously nothing is getting ionized and, or transitions into a different state, which for us is the main thing. So that's not quite the same thing, but it is not completely unrelated either. Okay, so methods for cosmological radiative transfer. First of all, yeah, the first method, general kind of class of methods rather, is ray tracing. So ray tracing, basically what it does is say, okay, so light propagates as rays. So I start from a source and then I propagate rays outward from that source. And along the way, I take into account, okay, how much of the light gets absorbed, how much maybe some additional one gets emitted if there is another source, and I figure out, okay, so what's the effect of this source at this point? So there are two types of ray tracing, so-called long characteristics versus short characteristics. So these are code words in a sense. So long characteristics is what's described here in this picture. So you start from the source and you go to every cell on the grid. So you get from here to this cell, from here to that cell, from here to that cell, and so on, all the way, and you calculate, okay, so how much of the stuff gets absorbed along the way, and you figure it out. So that kind of method is, in principle, very precise, but also not very efficient. Why? Because close to the source, you pass through many, many, many times, because all these rays pass through these cells. While outward, in some cells, you may not have any rays at all, or you may have only one. So you don't know what's happening, or at least not very well. So in order to know everywhere, you need to send even more rays, which means that here you have even more than you actually need, while out there, you still may not have quite enough. So there are some issues with that. In principle, it's a very precise method and has been done, but in practice, there could be some issues that you need to be careful with. There is also so-called causality. Basically, what happens to this cell depends on what happened to this cell before. Why? Because if this cell was not very transparent, for example, most photons will be absorbed by it. So there is not much left for that cell. So you cannot do that cell before you do that cell, obviously, right? So if I am emitting light, for example, and I want to see, okay, how does this propagate? In order to get to you, it needs to go through the desk, maybe. And if it does, then obviously it will be absorbed, so it will never get to you. So the same principle. And then you need to have something called photon conservation, which is important. Why? Because in principle, photons should be conserved in the sense that not that photons are forever the same, but whenever you emit a photon, it either gets absorbed or it doesn't. It cannot just disappear, right? So if you count how many photons have I emitted and subtract how many were absorbed, you should get how many did get there. And if these three numbers do not add up, then you have a problem because nothing will work properly. So you need to have photon conservation, otherwise things won't propagate correctly. And because codes are both discrete in both space and time, they are not continuous. They have cells or some kind of elements, spatial elements, and also time steps. You need to assure photon conservation on both. So one way to do this is actually, okay, let's not go into this yet. I forgot to tell you about short characteristics. So long characteristics is you start from the source and you just go through all the way and you calculate everything. Short characteristics is a little bit different. So you start from the source, but you only go to the next cell. And then what you get as an effect on the next cell is actually a kind of weighted average of these two cells affect this cell. And then you get the weighted average of these two cells will affect the next cell and so on. So you do a kind of interpolation along the way. So how this helps is that you get uniform average of space from the source to the cell, because you are always only propagating to the next cell and then to the next cell, and between these two cells you get the next one, and between these two you get the next one, and so on. So you get uniform, you always get one ray per cell. But the negative is that when you're doing the interpolation, you are smoothing out things a little bit. So maybe your directions won't be quite right and things like this, so you need to be careful. So that's called short characteristics, and that's what's happening here. And the method that we'll be using for the exercise, which is our code for tomorrow, it's actually using this short characteristic ray tracing. So just to let you know, and we'll discuss the method a little bit more later. Okay, so this is the short and long characteristics. So what about the photon conservation? Well, first of all, you need a photon conserving version of for spatially discretized radiation. So if you write the photonization rate like we did before, you get a formula like this. You have the luminosity, which is just the power, energy per unit time, cross section, and the absorption along the way, and then you dilute it with the geometric factor, which is fine, but it's a point, at a point somewhere. If you have a spatially discretized, what you have is not a point, but you actually have cells, right? So you have your grid like this, and you want your sources somewhere, and you want to propagate in this direction, and this direction, and you want to have a guarantee that the photons are conserved as you are doing that. And the local version won't do that. So you need to generalize it for finite volume being the volume of each cell. So you have that this is the, so you calculate, okay, what is the flux entering the cell? What is the flux exiting the cell? You take the difference between these two fluxes and divide them by the number of atoms in the cell. And this gives you the photonization rate. So that's what's written here. So this is the number of atoms in the cell. And this is the difference between what enters and what exits, because this is the differential optical depth through the cell. So if you're using this photonization rate rather than this one, this guarantees that you are conserving photons in space. So everything will then propagate at the correct speeds and so on. What about the time discretization? Well, for our code, there are different ways to do it. One way to do it is just take short time steps. So the time step for a photon, the time for a photon to cross a cell is just the size of the cell divided by the speed of light, because photons travel at the speed of light. So if you have fast ionization front, that makes it hard to track. You need to make very small time steps forward. And photonization time is 1 over the photonization rate, which is given by this kind of expression. So this is the number of neutral atoms divided by how quickly they change. So that's the time scale for the ionization of the cell. So if the photonization time scale is much smaller than the time scale for the ionization of the cell, why is this a time scale? Do I need to explain, or is it obvious? So that's a normal way to calculate time scale. So basically, you have a certain amount of money, right? And you're spending some money every day. For how many days you have money, right? So this is how much you have. This is how quickly you spend them. When you divide the two, this gives you the time scale on which the money will be gone. So it's the same principle for any other quantity. So whenever you want time scale for anything, you divide how much you have, divide by how quickly you spend it. And for the photonization rate, it has, again, dimensions of 1 over time. So the photonization time is 1 over the rate. So anyway, if you the ionization time is very short, then you need very short time steps, and that's not efficient. You can do it, but it will take forever, and your computer will slow down, and maybe you'll die of old age before your simulation is done, which is not a good thing. So you want to do it faster than that. So our solution to that was to average the photoionization rate over time and use this averaged one in the equation for the chemical evolution. And this gives you basically a good approximation to the result. Okay, so just to, how much time do we have? We still have, fine. Another kind of related method, but a little bit different, is so-called Monte Carlo radiative transfer. So you know Monte Carlo generally is word because of the Monte Carlo casinos and all that. It's a word whenever something random is happening or probabilistic, right? You call it Monte Carlo. So what is random here is you say, okay, so I have light and I'm emitting light from my source in all directions. So instead of doing this deterministic race and I just calculate along the ray like we did before, I'll say, okay, lights are just packets, and I just randomly say, okay, I send packet this way, then I pick another random direction, send the packet there, send the packet there, you know, and send many, many, many packets so I can sample the space around. And if I do enough packets, I can calculate, okay, so what's the optical depth? I can absorb it somewhere, and this gives me the final results when I probabilistically absorb it based on the local density. And if you send significant number of packets, this gives the photoionization rate, and then you can solve the chemistry like we did before using some kind of solver for the differential equation. Packets could have different frequencies, so you can do different spectra. You can have high energy photons, low energy photons. Why does this matter? Is because the cross-section depends on the energy, if you remember from the previous lecture. So high energy photons usually have much lower cross-section, low energy photons have higher cross-section. So that's important. And you can also solve the energy equation, temperature, and so on. So here is one example, very old paper, but one of the very widely still used codes for this type, which is done by, was developed by Benedetto Ciardi and, well, many other people since then, but this was the original one. So you can see that it works quite well. It gives you a little bit of a kind of not fully spherical regions, and that's a sign that maybe you didn't send quite enough packets. That's limited by your computer capabilities, obviously. If you send more packets, it will become more spherical, but something to be kept in mind. But otherwise, it works well. You have two sources. They expand the H2 regions. They merge the ionized regions. And then you get this total region. And of course, in 2003, computers were a lot slower than they are now. So this was a significant achievement to do at the time. It's still used, of course, much better code now. And finally, there is this moment-based radiative transfer methods. So basically, the principle behind them is that light is treated as a fluid. So why? Well, first of all, because the equations for the radiative transfer are not completely different from the fluid equations. If you write them in terms of the moments of the radiative field, and if you remember your fluid equations, they are kind of similar mathematically in form. So if you know how to solve the fluid equations, which very often you do because you do hydrodynamic simulations, you just use exactly the same methods to solve your radiation equations. And if you do that, you can get simulations like this, which is actually the largest radiative hydrodynamic simulation ever done, which we did a couple of years ago, our group. I'll explain a bit more about it, but basically what you need to do here is that you solve these equations, which are the first and second moment of the radiative transfer equation. Now, that's normally not enough. Why is it not enough? Is because, okay, so let's say I know the source function because that's the property of my matter, but I still need to solve for E, for F, and for P. So I have 3 unknowns and not enough equations, right? So in principle, that's not enough. So you still need to include more equations, so the higher moments. But if you include the higher moments, this means you include more equations, but then even more unknowns, and so on, until they become infinite number of equations. So of course, you cannot solve infinite number of equations, so you don't even try. So what do you do instead? You say, okay, I stop at the first 2, and I add some other relation which will give me enough equations to solve. And this is called closing relation. And there are different closure or closing relations. So one of them was developed a long time ago, is so-called optically thin Eddington tensor, which I'm not going to the details, but basically the Eddington tensor looks like this. And there is, yeah, optically thin approximation. So that's not optically thin gas, it's optically thin Eddington tensor, which is not the same thing. It's a bit complicated. I'm not going to go into the detail, but once you include this additional condition, there is another one which is called M1 closure, which is even more complicated to explain, which is used in this simulation actually. But either way, you get additional equation, then you can solve these equations and get your radiation. Now, what are the advantages and disadvantages of doing that? Well, the advantages are that unlike the ray tracing, which depends on the number of sources, because you need to trace from each source to each cell. So the more sources you have, the more tracing you need to do, which clearly, if you have a lot of sources, you need to do a lot of tracing, and that quickly becomes expensive. Here, there are no sources. I mean, there are sources which emit the radiation, but in the equations, once the radiation is emitted, it just enters this photon fluid, and the photon fluid just propagates like any other fluid. There are fluxes between the cells and so on, and it just follows the equations of the fluid dynamics. So once you add the flux to a cell, it's added. So you add it from all the sources that shine on that cell, and that's it. And then you follow it like normal fluid. So it doesn't scale with the number of sources. If you have more sources, you still do exactly the same work. So that's a big advantage, and that's why we have been able to do this big simulation, which is 8,192 cube grid and the same number of particles, and it's done with the radiation, hydrodynamics, M-body, everything. So you can do all this. It's still very expensive, but it's doable. However, it's not perfect. Why is it not perfect? Well, in the simplest possible kind of explanation, light is not a fluid. Light does not propagate like a fluid. So imagine I have some fluid and I flush it around. It doesn't propagate like light. Light propagates always in certain direction. Fluid just goes in all directions, right? Imagine this room is free of air, and I put some air here. How would it propagate? Well, it will just diffuse in all directions, right? But light doesn't do that. If I put some light shining in some direction, it will only be shining there. It certainly is not shining there, so it will never propagate there, right? So light cares about direction, fluid doesn't care about the direction. And so they are not the same thing. And this may or may not be a problem, but again, you need to be careful how you're using it and be aware that there are approximations going in. And these approximations make your answer potentially incorrect if you are not careful. So you need to be aware of these issues. But on the other hand, as I said, it's very fast. it's easy to scale up. You can use it also on GPUs or other accelerators. So there are advantages. It's still expensive, but you can do amazing things as long as you are aware of the limitations of what you're doing. And a little bit more about this simulation. So for example, here, what's shown is the temperature. So if you see a pinkish regions, these are supernovae blowing up in multi-million degree gas. They're around the galaxies. The galaxies are in the nodes of the cosmic web. And of course, radiation propagates over time everywhere. So if we, oops, went to the wrong way, but okay, let's show it again. So here, okay, so coming back to that, so what you are seeing here is the temperature. So you see this flickering, which is the feedback from reionization, which suppresses the local sources. So that's why they appear and disappear. Star formation gets suppressed, but slowly it's kind of ionizes everywhere. And where the sources are, of course, gets ionized faster. Well, where there are no sources, at the deep voids, it gets much slower. So as I was saying before, the moment-based methods do not scale with the number of sources, so they are potentially faster, at least for large numbers of sources, but also have issues. So first of all, you have that so-called courant condition, which basically says that your numerical method will become unstable if you take too long time steps. So you need to take time step which is shorter than the characteristics time step to cross a cell. So usually the speed of sound, the size of the cell divided by the speed of sound. In this case, though, it's the size of the cell divided by the speed of light, because that's the speed of your light fluid. And that's, of course, very short because light travels very fast, much faster than sound. So this means that the current condition dictates that you make tiny, tiny, tiny time steps, which is very, very, very expensive. So there are two ways to solve it. Either you say, okay, let's assume light actually doesn't go that fast, which, as you can imagine, is a little bit shaky physically approximation, but it works as long as you are aware of the pitfalls. It has some issues, but overall can be made to work. Or you can do hardware acceleration with GPUs, and like we did in this simulation, just use the full speed of light and very short time steps, which you can do, but then you have to make many, 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 many time steps. And well, the GPUs help with that. And the other issue is because light does not propagate as a fluid, light is not a fluid, there are issues with shadowing. So for example, if I'm sitting here and you can see that behind me there is a shadow, right? Well, it's not very clear shadow because light coming from all directions, but you know what shadow looks like, right? Well, in this case, there are almost no shadows. Because fluid, you can imagine if I'm sitting in a stream, the stream goes around me and goes behind me right away, because why not, right? That's how fluids behave. But light doesn't do that. Light, if it hits me, that's it, right? Doesn't go behind me. So clearly that's an issue. And sometimes it doesn't matter, sometimes it does. It depends on your problem, so you need to be careful. For some problems, you don't care, like here, it's not too important, but in other problems might be important. Okay, so coming to the testing and verification of the radiative transfer codes, we're almost done, so just bear with me a little bit more. As I said before, it's nice to be able to compare to exact solutions, and then also you can compare to other radiative transfer codes. So some problems have exact solutions, and the simplest of all problems that was solved a long time ago is you have a source in a uniform medium, and it's expanding a nice region around itself. So this was solved by, initially, I think, by Bernd Strömgren And that's where the term Strömgren sphere comes from. This was in 1933, I think, almost 100 years ago. And in this case, you can write analytical solutions. So the propagation of the ionization front is exponential, and then it stops. Why does it stop? Is because at some point, as you are expanding, your sphere has more and more atoms. So there are more and more recombinations happening. So basically, once the number of photons supplied by the source equals the number of recombinations happening in the sphere, they balance. So there is no more photons reaching the sphere, so it cannot expand any further. So that's called Strömgren sphere. And that's why if nothing changes, basically, it will stop. And the velocity you can calculate from this expansion. And the velocities kind of also have some kind of exponential behavior going down to 0 since it stops. And you can see that we tested our code for different time steps and so on, and we can get the behavior correctly. So that's just our code against the analytical solution. You can also do other problems where you know what will happen. So one of these problems is you have a clump which is much denser than the surroundings, and you are shining on the clump from one side, and then you should form a shadow behind. And you can, and the shadow is not perfect in the sense that some on the sides there is much less column density on the edges because there is much less gas along the way, because that's not a brick, it's a semi-transparent material, right? So there is a little bit of light in the edges, but then you should get a shadow behind. And you see that some codes get a shadow, some codes don't. Or they all get some kind of shadow, but not always perfect one. But anyway, you can compare. By the way, all these problems, if you manage to install our code, we'll run all these problems tomorrow. You can run them yourself and see the results with the clump and everything. But you need to install the code, so please do. Okay. Okay, I think we are done here. So any questions? Yes.
So you mentioned that it depends on the problem statement whether you treat light as a fluid or not. So will you please give some examples?
It depends on what, sorry?
You mentioned, right, that in some, it's okay to deal light as fluid in this moment-based method. And
yes.
so sometimes it goes behind the object,
yes.
and sometimes it is not relevant to think about this problem. So can you give examples when it becomes relevant?
If you have, well, this is one example, right? If you are interested, okay, I have a clump and I want to see the shadow behind the clump. Right, so for example, if you see the, look at the Eagle Nebula, for example, famous Hubble picture of the Eagle Nebula, there you see clear clumps because there is turbulent medium around and there are shadows behind it. If you try to do this with a code that doesn't do good shadows, you'll fail because shadows are all there is. You literally not see the picture because you are interested in what's happening in this case. Well, in cosmology, that's usually not that critical because in cosmology, things tend to move around. So they appear, disappear, move around. So the shadows are anyway not permanent in any case. So the fact that you don't make very good shadows very often doesn't matter too much. But again, it's an approximation. They all have approximations. They're just different kinds of approximations, but ideally, if you care about the shadows, you should not use a fluid-based method because fluids don't do shadows. Well, ray tracing does do shadows. Ray tracing, on the other hand, might be more expensive or may have other approximations. Actually, not may have, it does have other approximations. So again, you need to be careful. Some methods, there is no perfect method. If there were, everyone will be using it. But there isn't because it's a very hard problem. There is always approximations. The whole physics is like this, but here is quite obvious anyway. But depends on your problem. You need to be aware of. If you have relatively few sources, for example, moment methods may work okay, but they are more expensive because they have a lot of startup costs. While ray tracing for few sources is instant, as you'll see tomorrow if you run the code. You'll do it in literally minutes. You'll do the whole simulation with few sources on your laptop. It doesn't even matter how good laptop you have. I guarantee you'll do the whole simulation in a few minutes. Well, this may not even fit in your laptop because it requires more memory, more calculations. It's more complicated. Once you have millions of sources, this is cheaper. But yeah, depends.
How to choose which ray tracing method is more effective for a particular problem?
Well, it's more art than science. You need to try. Basically, obviously, different people choose different things and they all work at some level. I mean, no method is bad, right? They do work if people use them. We have chosen, for example, ours because we wanted something that's doesn't have the issue with the long characteristic ray tracing where you have too much sampling nearby the source and too little outside. So in this case, if you don't send enough rays, your H2 regions instead of a sphere could look like a hedgehog because you get rays in some directions, in other directions nothing, and it starts looking like a hedgehog, which obviously shouldn't happen. You can avoid this by sending enough rays, but then it's question of, okay, maybe that's too expensive, so maybe it's precise, but too expensive. So ours was balanced between having it reasonably efficient and still good. But there are hidden things. So for example, as I said, it's more diffusive, so you need to do some tricks to avoid this kind of thing, to diminish it. So if you read our paper, all these gory details are explained in full detail, but in any case, there is no single answer. If there was one perfect method, as I said, everyone will be using it, right? It just, some methods are good for one thing, some for another. Maybe you like solving the fluid equations better than solving the ray tracing equations. So you just do the fluid method like was done here, and that's perfectly fine. And we use this and the other one, and it's not an accident because for this kind of thing, this is better because it's already working and the other method might be too expensive. So there is no ideal way to deal with these things. It depends on your problem. It depends on how good computer you have, how well you have parallelized your code. Can you use it on GPUs or not? We used to not be able to use it, our code, but now we can. So it's a lot faster now, like hundreds of times faster. So if you have GPUs, by the way, by any chance on your laptop, you can use the GPU and do it much, much faster. But even if you don't have a GPU, that's fine. You still can use the code. So it's very flexible, but well, we have been developing it for 20 years almost. So wasn't always like this. Yeah, maybe it's not a very satisfactory answer, but as many things in physics, there is a bit of art and intuition and so on, not always a strictly mathematical way. Okay, this is the best thing to do. Question?
Yeah. Can you go back just one slide?
Yeah. This one?
No, one slide.
Yeah, this is
just yeah, one slide. Yeah, this one.
This one.
So if you see this ionization bubbles, there are those are confined with this white regions, and there are another black ring type of thing. So what is that? How is it?
Yeah, that's a bit of a puzzle for younger people in the audience, but The reason for this was that at the time, color figures were very expensive in journals. So people were publishing in black and white. If you look at the color, these are just different colors. And because photons have different energy, this just shows how far they are penetrating into the neutral region. So these are just different colors. This is fully ionized, and then it kind of color gradient. So these are the different colors, but of course in black and white, it just looks ugly. I should have found the color figure, I guess, but it's a bit tricky because the one that was published was the black and white figure.
Back to the last slide, I think there, this is somewhat clear.
The other way.
Last slide. Last.
Yeah, well, I'm trying, but movie playing. Let's hope it doesn't crash. It's a nice movie, but
Yeah.
that's not the idea. And the movie again. Okay. Yes. Is that? No, that's not the last.
Yeah.
That's the last. Yeah.
Here also you can see, I think sometimes that color variation is there. I think the upper panel right side one and the
This.
right side. Yeah, there is also a dark patch. If you see the color variation, so it's, yeah.
So the reason for this one, this is actually, it's difficult to read, but this method here is called RSPH, radiation SPH hydrodynamics. So basically things are done in particles rather than cells. And with particles, it's very difficult to make a spherical clump that's uniform. So there is some, it's not quite symmetric, and there are some issues with just, it's not issue with the code, it's issue with the test being set up easily with particles, because particles don't tend to do perfectly uniform spheres, for example. This code here is actually the same one that we saw with the color gradient earlier, this mountain. That's our own C2 ray, but the previous version, not the one that we'll be using tomorrow. And these are some other ones that, well, existed at the time. I'm not sure they're all used yet. But you see that for all of them, the shadows are quite different. So some of them, there is a little bit leaking in the shadow. There is sometimes quite a bit of leaking, sometimes less.
Yeah.
They're all, yeah, different. The ray tracing tend to agree. So these two are both ray tracing. You see that they're almost identical. This is also ray tracing, but because of the particles, it's a little bit funky. And then these other ones, yeah, it's complicated. We have a whole long paper you can read about this. It came, yeah, quite a few years ago now, maybe 10 years ago or so.
Hi. So I wanted to ask, if we want to do parameter inference using these simulations, then do you think faster RT methods will be more beneficial, or using emulators like they did with Licorice?
Yes, that's what we're hoping, because now, I mean, for our code, for example, now that it can run on GPUs, you can literally run whole simulation in hours, maybe even less, depends on the simulation and how good your GPUs are. But yes, you can, in principle, run thousands of simulations and run, create emulators, do inference, yes. It used to be too expensive. I mean, before we only had at most like tens of simulations, so it wasn't feasible. But nowadays you can, yes. And we want to do that as one of the next things to do. You still need a lot of GPUs, but it's doable. Yes.
Very nice talk, Professor. So I had a quick question. So in a few slides back, you had showed the comparison between different numerical-based techniques to solve radiative transfer, right? The
Yes.
3x4
Well, that's also
plot.
one of those
Even
tests.
this.
Yeah, yeah,
So
sure.
I was just wondering, how does any one of those numerical-based technique compares to the semi-numerical techniques that most of us use? For example, 21 centimeter fast, or I mean, like the semi-numerical based ones should definitely do worse than numerical based. So was there any study done that quantitatively?
There have been a few, actually. Professor Suman here has done one of them. Semi-numerical methods are obviously more approximate, so they usually use much coarser cells because various technical reasons that we don't need to go into. I mean, ultimately, it comes down to counting photons, and sometimes they don't, for example, count photons correctly, so that's one issue. Obviously, you should never rely on semi-numerical methods on small scales because this will never work properly because they're not set up to do that. I mean, this you cannot do with semi-numerical method. It's just nonsense because you cannot do it. On large scales, on average, kind of coarsened scales, they're not too bad, but you still need to make sure that you get all the physics correct. For example, recombinations and varying recombinations, subgrid physics, clumping, other things. There hasn't been very detailed